In the last video, we talked about images, kernel, and the mapping of the linear mapping. Now, in this particular video, we are going to talk about affine spaces. Affine spaces are are the spaces which are the subspaces that are after being a subspace, after finding a subspace. When you shift the entire subspace away from the origin, then that particular space or that particular set of vectors is called affine space. Affine spaces are not vector spaces because they do not have origin, because they are shifted away from the origin. So now they are having certain offset. So they are shifted by a particular thing or particular vector, and that particular vector is called a support point. So now you can see this red, you can see this uh, red thing is a vector space because it is passing through the origin, and by a purple vector we have shifted it. And it again becomes a line. So all the points on this red line are shifted to this dark blue line by this purple vector. By adding every vector, we are adding the purple vector to the every vector on the line, red line, and then they are going to shift it on the blue line, right, or the black line. So if you are getting it a black, so let me just focus it. See, so every point when that is shifted, every point on the red line, when that shifted to the blue line, then uh, by with the help of a purple vector, it will get shifted to the blue line, and that is called the affine space. So earlier the red line was a subspace, but now the blue line is not a subspace because it is not passing through the origin. So that is the definition of the affine space. And this purple vector is called support point. The mathematically we say that the affine space A is a set of vectors uh, of set of vectors in the such that there exists a vector in subspace V. So because we are talking about a subspace V and we are looking for a x naught vector which is in the vector space, the original vector space. So there is some vector space W, and then there is a subspace V, and in that subspace V you take every vector of the subspace V, you add some vector of vector space W to each and every vector. So this x naught is the vector of W, the larger vector space or the largest vector space of that kind. So this x0 is coming from that vector space, and you add the elements, add every vector of V, add every vector, add this particular x0 to every vector of V, then the set of vectors formed is called affine space. That is the definition of the affine space. Now let us suppose that we have two affine spaces L1 and L2. We have two affine spaces. So let me take this cyan. Okay, fine. There are two affine spaces L1 and L2. So L1 is represented by red color and L2 is represented by the cyan color. In the diagram you can see here. Yeah. So this is the diagram. Now you can see that L1 is defined by, this is the affine space corresponding to the purple plane. So the red plane is shifted by x 2 vector. So x2 vector, so every point in the purple plane is added with the x2 vector, that is the black line, and then the entirely they are shifted to make another plane passing through x2. And similarly, there is another subspace corresponding to L1, represented by cyan color. Between the red color parallelogram, you are finding this cyan color. So cyan color, this is the cyan color. So sorry, this cyan color is the subspace, the L1 space. So it's an affine space. It's not a subspace, it's a affine space shifted by vector x1, that is the blue vector. So the support point for this green subspace, green is the subspace and corresponding affine space is the cyan colored. So it is shifted by x1 vector. So every point in the green color subspace is shifted by x1 so as to make the affine space made by cyan color. Similarly, the purple color space, that's a subspace, and that every point in that subspace is shifted by the black vector, the x2 vector, and they are now shifted to the red surface, red plane. And this red plane is L2, and the cyan color is L1. Now, definitely, both the points are actually, if L1 is the subset of L2, if L1 is the subset of L2, then definitely the point in the cyan color, any point, any vector in the cyan color and any vector in the red color, they are definitely in the red color surface. Both the points are in the red color surface. Now, if you subtract these two vectors, then definitely they have to be, the vector has to be parallel to the, or the vector has to be an element of the purple surface or the U2 subspace. So that's what here we have written. What is this thing? Consider two affine spaces L1 and L2. When U1 and U2 are subspaces of V, then the affine spaces also follow the subset property if and only if, first of all, U1 has to be the subset of U2, right? So if U1 is not a subset of U2, then definitely means L1 cannot be a subset of L2, right? Because they are not in each other. So definitely, if they are not in each other, then their affine spaces, the corresponding affine spaces, they may intersect, but they cannot be completely inside each other if they are not subspaces of each other, right? So one thing is that. The second point is what we have said, x2 minus x1. So any 2 points in the red space, if they are subtracted, so the x2 is 1 point in the red plane and x1 is also 1 point in the red plane, and if you subtract both of them, x2 minus x1 or x1 minus x2, then definitely that particular vector will be in the purple subspace, that is in U2, and that's what it is written here. That's what we are finding it here. Okay, so let us suppose if any vector space U you have, and it's a subspace U, so it must have some basis. So let us suppose it has a basis defined by okay, let me take the red one, defined by these vectors. So we can represent any vector in the affine space by this. So the subspace, the point in the subspace can be defined by this, and the point in the, now we shift it by b1, sorry, we shift it by x0 so as to make the affine space. So ultimately this particular thing represents any vector of the affine space with respect to a subspace U uh, and passing through x0, the support point. This particular representation is called parametric equation of L. So the affine space, so any point in this affine space can be defined by this parametric equation, this one, with respect to the directional vectors, the basis vectors, right? Now you might remember that the same case was there when we solved an inhomogeneous system of linear equations. We said all possible solutions can be given by the particular solution plus homogeneous solution. The homogeneous solution is a subspace because it comes from the null space or the kernel space, that is by solving Ax is equals to 0. So this particular xh, all possible solutions of homogeneous system of linear equations makes the kernel space or the null space, and that's a subspace that we have proved in the last part. Now when we are adding a particular solution to it, we are actually making it a affine space. So that's how we are saying that the solving of inhomogeneous system of linear equation is equivalent to making a affine space. Now let these be the linearly independent vectors of the vector space V, and let us suppose that vector space V, the dimension of vector space V is P. Then any hyperplane defined by this makes a subspace, and when we add some x0, the support point, then it becomes a n-dimensional subspace, or sorry, n-dimensional affine space, right, with the support point to be x0. Now similar to the affine space, we can have affine linear mapping. Instead of the normal mapping, in this particular part, in this particular thing, what happens is that we have a mapping with input space V and the output space W. So V and W both are the vector spaces, but now we have mapped it to phi of x. So let us suppose that this phi is a linear mapping. This phi is a linear mapping. Now if this phi is every item of, after applying the mapping phi, if we shift or if we translate it by a vector, again the support point, then it is called affine mapping. Because if phi is linear mapping, then origin of vector space V will be definitely be the origin of vector space W, that we have proved in the last part. But now what we are doing, we are actually shifting this every vector of image by vector A. Now this becomes the affine mapping, and now it may not have, or it will not have the origin vector if there is a condition. So there is a condition that we can talk later, but if we shift it by certain vectors, then definitely it will be a affine space. So you can assume that an affine mapping can be written as a composition of linear mapping xi and a translation tau. So while first you have mapped, so it's a linear mapping, so you first map every element of V to W, and then you translate or you shift every point in the image by certain amount. So that is the translation. right? So it can be seen in that way. Now, composition of any two affine mappings will also be an affine mapping. That is very straightforward, because you are you are mapping to. So if you are mapping two affine mappings, so basically if you are taking a composite function, so first of all you are doing a plus phi of w, where phi is a linear mapping, and then you again take some xi of a plus phi w, right? So if xi is a linear mapping, because I'm assuming that first you take, I'm assuming any linear affine mapping as a composition mapping of affine mapping, and then, sorry, linear mapping and then translation. So if I do the translation, if I do the first the linear mapping and then translation, so it will become a, and the composition is also become a affine mapping. It is easy to prove. You can check it out how you can prove it. Affine mappings are also some way interesting, because you can study them just by uh, taking them back to the subspace structure by subtracting certain vector, the support point, and they actually keeps the geometric structure invariant. So the geometric structure is not going to change, that will be preserved, and the parallelism of the vectors, it will remain same. That will also not change. So if it was earlier, it was a parallel, then after taking the affine mapping, it will also be parallel. So that's all for the this particular video. In the next video, we are going to talk about norms, uh, uh, and then dot product and all. Thank you. Thank you for the video.